Well, welcome back to our review on relative extrema, and we're also going to cover absolute value. So example 1, f of x equals x to the fourth plus 1 divided by x squared. So remember, our goal is to set the derivative equal to 0 and check to see if it's ever undefined. So my first move, and some of us have finally got this down and some of us still haven't, when there's one term on the bottom, we want to make sure we split. So I'm going to do it in very baby steps just to make sure we're on the same page here. So I'm going to rewrite f of x. I'm going to split x to the fourth over x squared plus 1 over x squared. So this becomes just x squared plus x to the negative 2. So I've done zero calculus at this point. I just rewrote these. So now I'll quickly take its derivative. So I've got f prime of x equals 2x minus 2x to the negative third. We'll rewrite that as 2x minus 2 over x cubed. Make a note that this x cubed is only on the x, not the 2. So at this point, I want to set the derivative equal to 0. The next thing I need to do, because I have fractions that need to be added, I need to get a common denominator. So I'm just going to multiply this by x cubed. So I will get 2x to the fourth minus 2 all over x cubed. So there's two things we have to catch. We have to set it equal to 0 and check when it's undefined, which basically means you have to set both the top and the bottom equal to 0 when you're checking for 0 and undefined. So 2x to the fourth minus 2 equals 0 and x cubed equals 0. So this again is when it's undefined, when the denominator equals 0, so obviously just x equals 0. Here I'm going to get x to the fourth, add over the 2, divide by 2 is 1, x equals plus or minus 1 when I take that fourth root. So now we'll just throw this on the sign chart. So in order, negative 1, 0, and 1. And I'm going to take a moment and just off to the side rewrite my f prime down so I recall what I'm plugging this into because I can't see it on my screen. So I believe I had 2x to the fourth minus 2 all over x cubed. So now these aren't as pretty to plug in. Obviously between 0 and 1 you're going to have to pick a fraction like 1/2. So again, all I need to know is if this is positive or negative. So when I plug in 1/2 in this denominator and I cube it, I don't care what the number is, I know it's positive. But now I have to be careful here on top. 1/2 to the fourth, well 1 to the fourth is 1 and 2 to the fourth is 16 times 2 minus 2. So this is 2/16 minus 2, which is definitely a negative, so I have a negative over a positive, which is a negative. And again, we'll plug like a negative 1/2 in here. I'm going to do the same thing I just did. If I cube negative 1/2, I definitely get a negative in the denominator. And basically, I'm going to get 2. If I raise it to the 1/4, I'm going to get 1/16 minus 2, which is also a negative. But a negative divided by a negative is a positive. And then I'll plug in a 2. I believe I get a positive, a negative 2, I get a negative. You can check that on your own. And we want to finish our sign chart. So some of us got lazy on this. We want to make sure we label the top f prime and the bottom f. F prime can only be answered with positive or negative because that's what its line says. F can be described as decreasing, increasing, decreasing, increasing. So you can state where you have relative mins, maxes, etc., and on intervals things are increasing and decreasing. So I guess just to make it very clear one last time, I will write this out with the proper justification. So I will say f has a relative max at x equals 0, and my justification is f prime, remember described as top row, changed from positive to negative. I should have a relative min, let's see, at x equals negative 1 and x equals 1. And again, my justification should be f prime changed from negative to positive. Okay, now one we haven't talked about yet is this absolute value, and you're going to see a lot of it this year. Basically, you've got to highlight this for yourself, is that absolute value must get sketched. That is huge. Star that in your notebook, highlight it. You can't solve any absolute value problem, whether it's a derivative or an integral, without a sketch. And the other thing to graph it is you just basically want to find the x and y intercepts and then remind yourself that absolute value makes a v, whether it's positive or negative, but we know we're making a v and we've got to sketch it. Okay, so here we start our first absolute value equation. So we said we can't take the derivative, we have to sketch this out. So basically we want to get our x and y intercepts. So the x-intercept, the y-intercept is the easiest, so I'm going to start with that. Y-intercept, so again, where I cross the y-axis, that means my x value is 0. So I'm just going to substitute a 0 into x, so I get 0 plus 2 minus 1, so that's 2 minus 1 is 1. So I'm going to go ahead and sketch this off to the side. I should have a y-intercept at positive 1. Now, the more annoying part is to get the x-intercept. So of course I'm going to set y equal to 0. So 0 equals the absolute value of x plus 2 minus 1. Now unfortunately they took this out of the Algebra 2 curriculum, so we did not cover solving absolute value in Algebra 2. And I'm not 100% sure if it's in Algebra 1 anymore, so I'm going to quickly review this. You may need to take a note off to the side. So typically to solve an absolute value, you get the absolute value by itself. So I'm basically just going to take that 1 and add it over. So the absolute value of x plus 2 is equal to 1. Now, to get rid of an absolute value, you have to take both the plus and minus. So basically, I have to stem this off into two equations and say x plus 2 equals 1, or I can say x plus 2 equals negative 1. So to get rid of an absolute value, you have to consider both the positive and negative. So if I solve this, I should get x equals negative 1, and x equals negative 3. So those should be my x-intercepts. So negative 1, negative 2, negative 3. I have 1 at negative 1, 1 at negative 3. Now, what else should you know about absolute value? Well, we do a ton, and I mean a ton of shifting in Algebra 2. So let's recall, anything with the x is your horizontal shift, and anything with the x does the opposite. So this actually goes left 2. And anything by itself here is a vertical shift, and it does what it says, so this goes down 1. So I know the vertex should be at negative 2, negative 1. So if I go negative 2, negative 1, that should be the vertex of my absolute value, and it was positive, so I know that it opens upwards. Alright, so these take a bit because we're not taking any derivatives, we're sketching the graph instead. So now we go ahead and we make our sign chart based off this sketch that we just did. So remember, the definition of our sign chart is where the derivative equals 0 and doesn't exist. Well, this is a graph of f. So if I want f prime, I have to look at the slope. So you'll notice this whole slope is negative, this whole slope is positive, so I don't have any zero slope. But right here, the slope does not exist. It comes to a nice corner. So my only critical point is going to be at negative 2 because that is where the slope did not exist. And just like we said, up until negative 2, it was a negative slope, and past negative 2, it was a positive slope. And I'm literally just looking at the picture that I drew. So I obviously have a relative min at x equals negative 2. F prime changes from negative to positive. So this next example I picked in particular because some of us are having a hard time pulling out GCFs. So, of course, we're going to rewrite this for ourselves as x in the quantity 9 minus 3x to the 1/2. And clearly we said times, so we have to do product rule here. So y prime equals first, derivative of the second, bring it down, keep the inside to that negative 1/2 times the derivative of the inside, so times negative 3, plus leave the second times the derivative of the first. Okay, so again, calculus is very simple. It's our basic algebra skills that we need to continue to work on here. So at this point, I'm going to look to this side of the plus sign and this side and pull out the GCF, the quantity that looks the exact same. So hopefully you've nailed it for yourself already, and it's obviously the 9 minus 3x. So I'm going to pull out 9 minus 3x to the negative 1/2. Now what's the next step? You make a nice bracket. So if I've pulled out the 9 minus 3x to the negative 1/2, I am then left with 1/2, negative 3, and x. Those are being multiplied, so that's negative 3/2 x. If I had a half of these, I took out a negative 1/2, I'm always going to have one of them left. Make sure you carry that plus sign down, so I'll have 9 minus 3x. So now my goal is just to clean this up. So I'm just going to start moving things. This has a negative exponent here, so it's automatically going to go to the denominator. So that's going to be the square root of 9 minus 3x. I'm going to add my like terms inside here. I have x's. I'm actually going to call this 6/2 because that's equivalent to 3 if I get a common denominator. So negative 3/2 and negative 6/2 make negative 9/2 plus 9. Alright, I can't leave a complex fraction, so to eliminate this, I can just multiply every term by 2, and this quantity by 2. So that's going to leave me with negative 9. Oh shucks, I lost my x. Sorry about that. Negative 9x plus 18 all over 2 root 9 minus 3x. Okay, so at this point, I'm now setting my derivative equal to 0, which of course means when you have a fraction, the numerator equals 0. But we also have to consider when a fraction is undefined, so we also have to set the denominator equal to 0. So hopefully here in your head, and subtract 18, divide by negative 9, you should get x equals 2. On this next part, just don't go taking square roots until you get the root by itself. So I have to first divide out the 2, and 0 divided by 2 is still 0. I can then square both sides. So I've got 9 minus 3x equals 0. Subtract the 9, divide by negative 3, and you should get x equals 3. Okay, so now to make the sign chart. My two critical points are 2 and 3. So a little close, so we know we'll have to use a fraction in there. F prime and f. And I'm plugging them back into this derivative that I'm circling up here. So again, I don't actually care what the number is. I just care whether it's positive, negative, or even doable. So I'm going to start with a 1. So negative 9 plus 18 is definitely positive, divided by 9 minus 3, the square root of that is positive. I would say I definitely get a positive here. So I'm just plugging it into these pieces, plugging on the top and the bottom to see if I get positives or negative. Here I'm going to use something between 2 and 3. So you're probably thinking like 2.5. I don't like multiplying by decimals. It's very hard for me. So I'll call that 5/2 right off the bat. So again, 2.5, the tens place is 10. That's 25 tenths or 5/2. So when I plug in 5/2 times 9 plus 18, I definitely get a negative. All over 5/2 times 3 is 15/2. 9 minus 15/2 is definitely a positive. So I get a negative there. Now watch what happens when I plug in a 4. On top, I definitely get a negative, but on the bottom, I get 9 minus 12, which is imaginary. So basically none of this exists anymore because we don't deal with imaginaries. We don't have to worry about that. So you can state your solution. We have a relative max at x equals 2. We have intervals of increasing and decreasing. All right, now on to the fun ones, the trig values. If you know your trig values, this is very easy. If you don't, flashcards are going to be a good thing. It's important that you know your trig values. So I'm going to take this derivative, of course, and I've got y prime equals 1/2 negative cos x, and I'm setting that equal to 0. So I'm going to say cos x equals 1/2. Okay, now, we practice this a lot in our summer bridge. Our domain is 0 to 2 pi. So basically you have to say to yourself, cosine, and this is positive. So all students tip cows. I need cosine to be positive, which means I can be in quadrant 1 or 4. So I have two solutions here. Okay, one answer is in quadrant 1, one answer is in quadrant 4. So you basically first have to get your reference angle. So I'm going to make a little note, my reference angle. What is the magic number that pops in your head? For what value of x is cosine equal to 1/2? So 30, 60, 45, or 0, 90, 180, 270, 360. hopefully you're saying theta equals 60. Okay, so what that means is you're going to go 60 degrees in this direction and 60 degrees in this direction. So in quadrant 1, that's 60 degrees, but in quadrant 4, that's 300 degrees. So I'm going to make a note. In quadrant 1, that's 60 degrees. Quadrant 4, that's 300 degrees. Now, in trigonometry, they want all of your answers in radians. So this is actually pi over 3, because that's 180 divided by 3. And now you're saying, okay, this is something pi over 3. How many 60s go into 300? Well, basically, kill a 0, and 6 into 30 is 5. So this gives me 5 pi over 3. So lastly, I just need to make a sign chart. So I've got pi over 3, 5 pi over 3. Now here's where we have to be careful. We had a domain there at the beginning from 0 to 2 pi, so you can't test anything negative or outside of that 2 pi window. Alright, so now again, it might be easier for you to think in degrees and then convert to radians after. So I need somebody before 60, which is obviously 30 degrees. Oops, where'd that go? 30 degrees. Whoops. Which again is pi over 6. So I have to test pi over 6 here. Here I need, and again, if you want to put degrees down to help yourself out, I need anybody between 60 and 300. I typically pick one of the made quadrants, like 90, 180, 270. So I'm going to pick 90, which of course is pi over 2. And 300 to 2 pi, you're going to have to pick somebody in there, a multiple of 30, 60, or 45. So I'm going to pick like 330. Okay, so I'm going to test pi over 6. Now I have to plug that back into the derivative, which was 1/2 minus cosine theta. So basically that's going to be 1/2 minus the cosine of pi over 6. So it's the cosine of 30, so that's 1/2 minus radical 3 over 2. So basically this is bigger than 1, which is going to tell me that's a negative solution. Then I'll do 90, so 1/2 minus the cosine of pi over 2. So now I'm picturing my graph to get pi over 2. That's a 0, so that's definitely positive. Now, here is one trick for you, and it only works in trig. These actually alternate. So this one will be negative based on the fact that this only works in trig. So now I can justify any relative mins, maxes, etc. based off that. So real quickly, I just want to touch base on a few more trig values. So let's take this first one. If I want to solve this equation, obviously I first need to divide the 2 out. So I have the sine of 6x equaling 1/2. So basically, I'm going to ignore this, and I'm going to say, when does sine equal 1/2? Well, first I'm going to get my quadrants. All students tip cows. It's a positive 1/2, so it's in quadrants 1 and 2. So for what value is sine equal to 1/2? So that's 30 degrees, or pi over 6. So I know I got to go 30 degrees this way, 30 degrees this way. So that's 30, and that's 30 away from 180 makes that 150. So how many 30s go into 15? That's 5. So I know I have pi over 6 and 5 pi over 6. And I'm going to set each of those equal now to 6x, which was the part I ignored. So I'm going to get x equals pi over 36 and x equals 5 pi over 36. Lastly, sine x equal cos x, that's a very, very common one. If I were to graph these two functions, clearly they intersect at 2 different moments in time. And basically you're just saying, when do sine and cosine have the same answer? So if you picture your table of values, 30, 60, 45, at 45, both solutions are radical 2 over 2. So I know one solution is pi over 4. So now I just have to think quadrants. All students tip cows. They're both positive in quadrant 1. Here one's positive and negative, so that's out. Here they're both negative, so they're equal. Here one's positive and one's negative. So it would also have to be in this third quadrant. So if I put 45 degrees in there, I would do 180 plus 45 to get 135, which turns out to be 5 pi over 4. So we'll probably work a lot more with trig because it's not going to go away, but we've got some good practice tonight. We'll see you tomorrow.